Good morning, class, and welcome to this lesson on Modern 6 de Broglie wavelength. Today we will be able to relate the momentum of a particle to wavelength. So, let's go back to let's go back and review a little bit here. So far, this concept of modern physics has really been about taking wave-like behavior and particle-like behavior and saying that these two are equal or they at least can be comparable. Okay, maybe not equal, but at least similar. Okay, so we have been taking classical physics and then combining two subjects that typically were not combined before. So in our last video, we talked about the Compton effect. And Arthur Compton basically stated that a photon has momentum. A photon has momentum. And he gave us his equation of momentum equals h over lambda. So we took a photon, which we thought was all energy, and was able to relate it to momentum now. Okay, so that was pretty cool. So far, everything we've talked about has been about taking wave-like things and assuming they have particle-like behavior. For example, E equals mc squared. We took energy and said that this energy can equal this much mass, or this much mass can equal this much energy. So what we've been doing was we've pretty much been going one direction so far. We've been taking things that are wave-like and saying they're particle-like. Now we're going to go back the other way. So de Broglie said, Louis de Broglie, said that, okay, if photons have momentum, or if photons have momentum like particles, can particles have wavelength like photons, like waves? Okay? And so he made the assumption that this equation applies not only to photons, but it applies to particles too. So the wavelength of a particle is going to be equal to h over its momentum, which you can see is the exact same equation with it just rewritten for momentum and wavelength there. So in terms of equations and in terms of what we can do in class, for example, we really have learned nothing new. Same equation. But what made this astounding was that we before said, okay, a photon can have momentum, but now we're going back and saying a particle can have a wavelength. A particle can have a wavelength. And this was later confirmed by Clinton Davidson and Lester Germer. And they basically set up a simple experiment. They sent electrons through a double slit. We had the double slit experiment. Young's double slit experiment, if you remember. And what we found from Young's double slit experiment was that waves diffract, and they end up getting a diffraction pattern. A diffraction pattern is very uniquely a wave characteristic. Okay, waves diffract. It's a wave thing. Well, we found that particles of the right size will also diffract. So they sent electrons through this double slit, and you can see after 100 electrons here in this picture, it looks kind of random. After 3,000, you start seeing some bands here, and then once you move it down, you start seeing actually a clear-cut diffraction pattern of where there would be constructive interference and destructive interference typically. So that's basically it. Particles can have a wavelength just like photons can have a momentum. Okay, but what we find here, based off this, if the wavelength is equal to h over momentum, as you can tell here, momentum is equal to m times v. Okay, now we know that h is equal to 6.626 times 10 to the negative 34th. Okay, now we're dividing by mass. Okay, so if anything has a significant mass, so anything above the mass of particles, like protons, neutrons, electrons, that's a negative, excuse me, you're really not going to see any wavelength, no wavelength. It's there, it's just that you can't see it. I mean, if we took a baseball going 13 meters a second about, and a baseball weighs approximately about 0.15 kilograms, we get the wavelength of a baseball is approximately 3.3 times 10 to the negative 34th meters. That's pretty small, and so we're not going to really see anything with a big mass. So all particles, all masses have a wavelength, but anything that's bigger than the size of these things, we're really not going to be able to see that much. Okay, so it's really going to start becoming evident when we get down to the elementary particle, the proton, the neutron, the electron, or even smaller than that. Okay, so one more thing I just want to point out, if wavelength equals h over momentum, wavelength for electromagnetic waves, wavelength for electromagnetic waves also equals c over f. And so depending on the question, you might be able to equate these two things to help solve your problem. Okay, so I don't know what the questions are going to say, but I just want to point that out, that wavelength for an electromagnetic wave, because we know that c equals wavelength times frequency, that might equal that, and so we can equate these two here. Okay, so that's basically it. De Broglie wavelength is basically saying that particles have a wavelength the same way photons have momentum.